Okay. Okay. Hello, everyone. This is Rrapaj from NERSC. Today we have the pleasure of having the part one of this training event provided to us by IQM on Introduction to Quantum Error Correction by Danny Bulmash, who is the education lead for IQM. Danny, maybe you could quickly introduce yourself and then take it as you go.
Sure. Yeah. So my name's Danny Bulmash. I'm the team lead for education and community at IQM, and I'll introduce IQM a little bit for those of you who aren't familiar. Um, but my background is that I have a PhD in theoretical condensed matter physics from Stanford, and then I had an academic career for a while through a few postdocs, and was a professor in the U.S. for a little bit, again doing condensed matter physics, and then moved to IQM. And so my job is really to help people who want to learn about quantum computing learn more about quantum computing wherever they are. Um, so I'm really excited to be here today. Thanks to NERSC for the invitation. All right, so let's get started then. So first of all, just a little bit of logistics here. This is a pretty big group. We got 135 people in the meeting right now. So if you could please put questions in the Q&A. I will not be able to monitor both the chat and the Q&A while I'm doing the talk. It's just too many things for me to look at. We do have a couple of IQMers in the audience who may be able to help out with some of it, but uh, um, that's the current state. So please put questions in Q&A. There will be times when I will offer to the audience a question that I'd like you to think about. So when that happens, feel free to answer in the chat. That's probably the easiest way to do it. There will be some points at which I will probably open things up for questions, at which case, as long as we have time, we can chat. You can turn on your microphone and whatnot, but it's going to get a little bit chaotic if everyone's hopping on the mic. So Q&A is the easiest way to do it. But thank you all for coming. Really excited to get into this material, which seems to be really timely these days. All right, so before I get into quantum error correction, just a little bit about IQM. For those not familiar, so IQM, we are a company that builds world-leading quantum computers, and our mission is to do this for the well-being of humankind now and for the future. So we are a full-stack superconducting qubit quantum computer company. So we do everything from QPU design up through control electronics and things like that, software stack, including support for lots of familiar quantum SDKs and algorithms and error correction. So we really work all the way through this, and with the aim of really being able to have all of this work together to accelerate the innovation. So just a little bit about us further, our customers are all over the globe. We've delivered 18 systems worldwide, and this is actually an incomplete map right here. I think this hasn't been updated recently. We've got a couple more machines that have been announced as well. And we've delivered more quantum computers than anyone else out there. So we're really excited to really get our machines out there. And so what are our machines? So we have 4 different products. One is called Spark. This is a 5-qubit machine that's on premises. So these first 3 are installed on premises in your university, HPC center, private company, whatever it is. We can install one of these machines on site. And so Spark is meant for educational use. It's a 5-qubit machine that's really meant for hands-on learning. It's an open stack where you can really dig into the machines, even at the hardware level. Radiance is our current flagship model, and this goes up to 150 qubits. And this is, our workhorse quantum computer. And our newest product, Halocene, is going to start at 150 qubits and go up to 1,000. Or thereabouts. And this is really an error correction experimentation machine. So we're going to be talking about error correction today. Halocene is really a place for people to experiment with hardware and QEC workflows. So lots of the things that we'll be talking about today will be very relevant here. Finally, IQM Resonance is our cloud platform. We have 3 quantum computers on the cloud right now, one 54-qubit, one 20-qubit, and one 16-qubit star machine, which is an unusual topology for superconducting quantum computers. And you all are going to get an opportunity to play around with Resonance if you would like. And speaking of which, if you want to do any of the hands-on demos, so we're going to have a hands-on opportunity to run a quantum error correction experiment on Resonance tomorrow. So please sign up here. You'll get 250 bonus credits if you sign up using this link. So definitely take advantage of that. In addition to that, I will be distributing an introduction to CRISP, which is the SDK that tomorrow's notebook is written in. I'll distribute that tonight if you want to play around with that and run some of those things on the quantum computer as well. So those will be simple programs that you can run directly on the quantum computer. So I'll leave this up for just another moment or two, but that's all I have to say about IQM for now, and we're going to pivot into QEC after this. And I'll bring this link up again at the end of the session, but please take that down, sign up. It's totally free, and you'll have recurring monthly credits in addition to these bonus credits that you get for signing up here. Thank you to whoever just put that link into chat. Let me make sure I've got Q&A up. Good. So I do welcome questions throughout this. I will try to notice when there are questions and stop and answer them as we go, but I apologize if it takes me a little while to notice and get to your question. All right, so what's the structure of this workshop? It's a 2-day workshop. And today, we're going to start with a big picture overview of quantum error correction. So why do we need quantum error correction? What is it? And what does the roadmap towards a full fault-tolerant quantum computer look like? So I am going to assume some familiarity with the quantum computing. I'm going to assume that you know what a qubit is and what some of the basic gates are, Hadamard gates, X gates, things like that. But that's all of the background that I'm going to be assuming for today. Basically, what is a qubit and a little bit on how you manipulate them. Then today we'll take a break, and then we'll shift to talking about simple quantum codes and decoding. So an introduction to quantum codes. We won't see our quantum codes before the break, but we'll get to the quantum codes after the break. And what is the core problem of decoding? And then we'll also see how decoders look. And this is both an overview of software and hardware. I'm not going to be digging into the technical details of any of this super deeply. The aim of this workshop is really to get you familiar with the general concepts of QEC and enough to run the experiment tomorrow. So really, I'm trying to get as the core theory that you need to understand the experiment that the quantum error correction experiment that we're going to be running tomorrow. Optional homework, which I recommend if you've never run a program on a quantum computer before, is available here. This is Intro to CRISP. It's very simple quantum programs that you can experiment with and run. There's both a notebook that has blanks on there for you to fill in and experiment with yourself, as well as a solutions notebook on that GitHub link. So please take a look at that. That's what that QR code leads to. Now, tomorrow, we're going to start with the surface code, which is the most well-known and kind of standard quantum error correcting code. And we'll talk about what it is. And we'll talk about the experiment that we want to run, which is a quantum memory experiment. So what that is and what we're trying to do. Then we'll have a hands-on notebook. And you'll get to run a quantum memory experiment on IQM Resonance. And then we'll wrap up and talk a little bit about future directions. So that's how things are broken down. Today's going to be a little bit more theory and scene setting, and tomorrow is going to probably almost half of the session is going to focus on running this hands-on notebook. So with that in mind, uh, what is the part of the talk before the break? So we're going to start out by talking about why quantum error correction, why we need it, what we're doing with it. We'll talk a bit about classical error correction, which is entirely a thing that's important. And we'll see why quantum error correction is a very different beast from classical error correction. There's a lot of complications in QEC that are not present in the same way for classical error correction. And then at the end, we'll talk about the road to fault-tolerant quantum computing and where the industry is headed in order to build a full utility-scale error-corrected quantum computer. All right. So if there are any logistical questions or anything like that, please throw them in the chat now. I'll pause for just a couple seconds. All right. If there's no questions here, then let's get started. Why quantum error correction? So let's start with why error correction. So it turns out that sometimes classical computers do actually have errors that are really quite significant. So the story here is that there was an election in Belgium a few years ago where when the votes were all tabulated, there was an inconsistency in the number of votes that were recorded. And it turned out that one of the candidates had exactly 4,096 extra votes compared to what they were supposed to have. And after extensive investigation, people had realized, well, first of all, 4096 is a special number. It's a power of 2. And of course, classical computers work with bits. Um, so that is, really powers of 2 are special there. And so people figured out that what had happened is that a cosmic ray from space, most likely, had come in, well, by definition from space, had come in through the atmosphere and had struck the classical computer and flipped a single bit in the computer. And so the vote count had one digit that was changed, and it happened to be in a place that was counting votes. And so 4,096 extra votes popped up. Now, this is incredibly, incredibly rare. This is basically an unheard of thing to have happen, but it can happen classically. And so there are errors that happen in classical machines. They're just incredibly rare, so we usually don't have to worry too much about trying to correct them. I see there's a few questions. Let me get to those real quick. So if we already have an IQM account, are we still able to get the resonance credits? You know what? So for that, the best thing to do, you can try using the sign up link with the same email account. If that doesn't work, you can try sending me an email and we can get that stacked up for you. All right, and how many error correction methods in the quantum world when we compare for classical computers? I think the counting of error correction methods isn't really a very useful way to think about it. So there are many different error correction methods in the quantum world. There are many error correcting codes, decoders, lots of different pieces of these here. And so I don't really have a good way to count the number of methods of error correction for either classical or quantum computers. But classical machines are sufficiently robust to errors that we don't have to do a lot of explicit error correction. It's kind of built into the hardware. That's not so much the case for quantum computing. There was a question about, do you use Qiskit programming language? So IQM machines do support Qiskit. The workshop or this workshop in particular, the Jupyter notebook we'll be working on tomorrow, will actually be written in CRISP, which is a fully open source language that is actually was developed by the Fraunhofer Institute, and IQM gives strong support for CRISP. But we do also support Qiskit. Are there similarities between classical and quantum error correction? Yes. Wait for the rest of the talk. And for cosmic rays happened in embedded systems too, how can we apply to the embedded systems? There are classical error correction methods. I don't personally know a lot about their applications to embedded systems in particular, but I would be happy to chat about that later if you can enlighten me a little bit more. All right. So this is why error correction is important in general. Sometimes noise from, for example, outer space can cause real things to happen in machines that you didn't intend, and you want to make sure that you have that you're very robust against these sorts of errors. Now, this is particularly an issue for quantum computers. So, in general, quantum gates operations on quantum computers in general have errors. So, for example, how might an error look? So this is a representation of the state of a qubit. It's the Bloch sphere. So we imagine that we have a qubit that starts out in state 0. And we imagine we want to apply a gate, an operation, which takes that qubit and rotates it so that it is in the state 1. Now, the problem is that errors can occur. It might not be a perfect operation. So for example, if we look at this one on the right, we could imagine that our quantum gate doesn't quite rotate the qubit far enough. And so instead, it's not quite at 1. It's somewhere a little bit away from 1 on the Bloch sphere. And this means that there's some probability that when we measure the qubit, we intended to measure only 1, but now there's some chance that we're going to get an answer of 0 when we shouldn't. And we measure so in general, errors in gates and other circuit components introduce some small chance of measuring the wrong state. And so the fidelity is the term for the chance that the measurement is correct after applying a gate. So if your fidelity was 100%, your quantum gate would be perfect. There'd be no error. But even ignoring things like cosmic rays and things like that, quantum operations are imperfect. So the thing is that the state-of-the-art fidelities actually seem kind of high. So IQM Emerald, this is one of the machines that we have on our cloud as of the operating state on July 23rd, had its single qubit gate fidelity 99.97%, and its 2-qubit gate fidelity median was 99.62%. These are numbers that are very close to 100%. And in fact, the world record for any platform of quantum computers is about 99.99% 2-qubit gate fidelities. That's the world record. So that seems like a pretty good accuracy, right? We're working with our qubits, and 0.01% of the time, our gates give us an error. The problem is that that builds up quickly. So imagine that you're running an algorithm, and your algorithm has some number of gates in it. So let's say that we have a fidelity for a single gate of 99.99%. So if we run an algorithm that has 10 gates, then that algorithm is going to run correctly 99.90% of the time. Okay, this still seems pretty good. 0.1% of the time we get the wrong answer. That's okay, just run the algorithm twice and we'll be okay. But as we start adding more and more gates, that fidelity of the algorithm starts dropping. We get by 100 gates, we have 99% accuracy. By 1,000 gates, we only get 90% accuracy of our algorithm. And once we get up to 100,000 gates, this has fallen down to 0.005% accuracy. So only 0.005% of the time do we actually get the correct answer. So that would be a real problem. If you want to run an algorithm and you only get the right answer 0.005% of the time, that's pretty bad. So the question is, what do we need? How many gates do we actually want? Well, perhaps the most famous application of quantum computing would be breaking encryption. So in order to break RSA encryption, current estimates say that you need a logical, we'll get to what that means later, circuit depth of about 10 to the 12 gates. So that's way beyond this. If we want to run our algorithm successfully 90% of the time, we need 99.999999999% fidelity. That's 13 nines of fidelity. And that's just ridiculously difficult. The world record's only at 4 nines of fidelity. We need 9 more nines of fidelity if we just try to run this directly. So there's just no way that that's going to happen. That is a wildly difficult engineering challenge if we just work by improving a single qubit by single qubit. It just won't work that way. Our engineers are amazing. They do wonderful things. That's too much of a task. So is that hopeless? Does that mean that quantum computing is useless? Absolutely not. That is where the idea of error correction comes in. And the idea of error correction is that we're going to take many physical qubits, so an actual qubit on your machine, and we're going to group them together so that several physical qubits become one logical qubit. It's the thing that you're doing computation on in your algorithm is the logical qubit, and each logical qubit is represented by redundant physical qubits. And we'll see how this lets us reduce errors. So instead of having to engineer our qubits to be really, 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 really low noise, we can use many qubits to reduce the effective noise together. So we'll see how that comes about in just a little bit. So with that introduction in mind, our goals for this part of the day. So we're going to describe how to use redundant classical bits to correct errors. We'll define some key terminology that appears in the error correction literature, compare quantum and classical error correction, and then describe some of the key steps and high-level challenges that are needed to develop a fault-tolerant quantum computer. Then, like I said, after the break, we'll see our first quantum codes and discuss decoding. So with that, let me take a pause to answer questions here. All right, so let's see. One person here mentioned things about what the estimates that I gave for RSA encryption. They said RSA encryption, this is a theoretical figure, practical number could be different. Absolutely. So when I said that the current estimate is that it's going to take 10 to the 12 gates to break RSA encryption, then indeed that's a current estimate. So there might be breakthroughs that bring that number down in the future. But even so, we're still at many orders of magnitude away from having fidelities that are sufficient to be able to do this. And so, yes, we're definitely going to want to bring these numbers down practically, but it would also be great. But also, we need to start bringing our fidelities up by using quantum error correction. So kind of come at it from both directions. Let's see. So do we get these errors even when we simulate the circuit instead of real hardware? So in principle, if you simulate the circuit perfectly, then you would not get these errors. The problem is that when you have a large number of qubits, it becomes exponentially difficult to simulate those circuits classically. So if you only have 5 or 10 qubits, you're probably going to be able to simulate the circuit classically. But the whole point of quantum computing is that once you get to about 50, 60 qubits, if you want to do a fully general simulation of the circuit, then you can't do that classically in any efficient manner. It's just going to take way, way, way too long for classical simulations. And so with enough qubits, the simulation doesn't get you anywhere. And you would not get the errors, though, in a simulation. The break will be about 15 minutes. There was a recent paper by Google that estimated only about 10,000 qubits will be needed to break RSA. I believe, I don't know off the top of my head, I believe that's an accurate number, but the question is how many gates will you need for that? So gates are operations on qubits, not qubits. So 10,000 qubits is great, but but you still need an enormous number of gates, something like 10 to the 12 operations on those 10,000 qubits. Um, let's see. Did you find a relationship between qubit counts and algorithm fidelity? That's not that there's no straightforward way to have a relationship between qubit counts and algorithm fidelity. What is the probability that cosmic rays interact with the quantum computer? Um, and result in bit flip or phase smearing. So I don't know that probability for cosmic rays in particular, but cosmic rays are not the leading cause of noise in quantum computers. There's a lot of other sources of noise, especially electrical and magnetic noise, things like, and other sorts of, as you're trying to interact with the qubits, that tends to cause a lot more errors than cosmic rays. The cosmic rays do cause errors in quantum computers. I don't know the rate offhand. Do algorithm fidelity percentages depend on the type of quantum computer? So what I'm doing here is I'm saying, suppose that your gate fidelity is 99.99%. So that is a number that can be characterized for any fidelity, sorry, for any type of quantum computer. So different quantum computers tend to have different gate fidelities. Some of them are a little higher, some of them are a little bit lower. Um, and even the ones that are a little bit lower have various advantages. The ones that are higher have some drawbacks. But this number, if you fix the fidelity, that's just a number that you can calculate for any quantum computer. And so you could have a superconducting qubit with 99.99% fidelity. You could have a neutral ion one with 99.99% fidelity, so on and so forth. So this estimate doesn't depend on the type of quantum computer. Just the fidelities of those quantum computers. Okay. Gates don't have a size. Gates are operations on quantum computers, on qubits. So, for example, a bit flip. So flipping a qubit from 0 to 1 is a quantum gate. So that is not an object. That's a manipulation of a quantum computer. Are errors in quantum gates due to the fact that all quantum gates are finite approximations? So maybe a better way to say that is that there's a sense in which quantum gates are a little bit analog. They're, for example, laser pulses or electrical pulses. So you can't control those with infinite precision, in which case you do get some error in the gate as a result of that. Um, so I think if that's what you mean by finite approximation, then that is a cause of error. The other thing is just that there's a complicated electrical environment around so not only can you not control quantum gates perfectly, but there's there's a little bit of the environment around the qubits changes the gate a little bit. There's a question about different forms of error correction for classical computers. So I'll talk about comparing classical and quantum. I'll get to that more as we go later. So if I need to develop a quantum circuit for a real world problem, but right now we can't write. So if I simulate it, it will be ignoring errors. So you can do noisy error. There are noisy simulators for quantum circuits. So yes, there are ways to simulate noise in a quantum circuit. Default simulators often don't have it, but you can do that. Okay, so I'm going to cut off the questions for a little bit right now to be able to move forward. But if I haven't gotten to your question, I will try to get that a little bit later. All right. So let's talk a little bit about classical error correction. So I'm not going to do complicated classical error correction, but what is classical error correction? Meet A and B. So here's a person. I can't draw. This is A. That's all you're getting. No fancier pictures. A has a computer, and A also has a bit, 0 or 1. And A is going to store their bit in the classical computer, and then walk away. Now, a little while later, someone else comes along, say B, and B reaches into that classical computer and pulls out the bit that A stored. And the question is, what bit does B get? Now, classical computers are very reliable, and so most of the time, if A stored in a 0 in memory, then B should receive a 0 from memory. Great. But that's not guaranteed. So imagine that there's some probability, call it P, that there are errors. So if there's an error, then that bit might get flipped. And so when B comes by and reads the bit from memory, B will read a 1. Now, whatever B reads, B is going to assume, most likely, that if B reads a 0, A actually stored a 0. And so that means with probability P, B is going to be wrong about what A stored and have no idea that that's the case, right? There's no way for B to know just by pulling a bit out of the computer whether that bit was flipped or not. So there's some error, and say it's probability P. Now, classically, we're pretty good at keeping this probability P very, very small. But imagine that we weren't, and we wanted to work and try to make to reduce that probability a little bit. So the trick is what's called an error correcting code. So let's say A wants to store a message of 0, or maybe a message of 1. A and B make an agreement beforehand that the message, which is called a logical bit, is going to be stored as something different. So if A means to store the logical bit 0, they're actually going to store 3 bits that are 0, 3 physical bits that are 0. And if A stores a bit that's 1, the message 1, a logical 1, that means they're actually going to put 3 ones into the computer physically. So the message 111 the physical bits 111 mean that the message is 1. And the physical bits 000 mean that the message is 0. So we're using 3 bits to store a 1-bit message. That process where we have an agreement of this sort is called encoding. So that's a piece of terminology that we're going to store for later. I also just want to mention that if you go from 0 to 1 in the message, that's called a logical bit flip. And in order to do a logical bit flip, the message gets flipped is 3 physical bits being flipped, right? To change the message, we have to to change 1 bit in the message, we have to flip 3 physical bits thanks to this encoding. Okay. I do see a question here about connecting to the no cloning theorem. Yes, there is a connection to the no cloning theorem here, and it's not going to be kind of the core thing that I want to talk about, but yes, there is a connection to the no cloning theorem. Good. All right. So why does this help us? So suppose that A stores the message 0. That's the logical bit. So A is going to store 3 physical bits, which are 0s. And if there's no errors, then B receives 3 0s and interprets that as A having left the message 0. Now, suppose that there is an error. What happens if there's an error in, let's say, the third bit? Then what message is B going to receive? B is going to receive the message 001. And B says, hey, 001 wasn't in our agreement. That doesn't mean 0 or 1. It means something else. So what probably happened? The most likely thing that happened is that one error happened and the last bit got flipped, right? Because if A had actually stored 111, we would have had to flip 2 bits to get to the message 001, which is less likely than what happens than flipping 1 bit, right? So if we go from 000 to 001, that's only 1 bit flip. Going from 111 to 001 is 2-bit flips. That's less likely. So B is going to interpret that as a 0. Now, imagine that we had a lot of errors, say 3 errors. It is possible that A's message would get flipped all the way to 111. So if B receives the message 001, B is going to interpret that A probably meant 0. But if B receives the message 111, B is going to guess that A meant 1 and get it wrong. But the key thing here is that 3 errors are less likely than 1 error. And so this situation down here where all 3 bits get flipped and B interprets the answer completely wrong is much less likely than the case where only 1 bit gets flipped and B still interprets the message correctly. So the point here, and there's a term here, which is decoding. And that's this process of taking the message that B receives, whether it's an agreed upon message or not, and interpreting that as what A was trying to store. That process is called decoding. So it's going from a physical message to a logical message. So imagine that that this encoding process is correct. So A always encodes 0 to 000 or 1 to 111. So the question is, how often does this help us? So if there's more bits, there's more errors possible, right? There's more bits to have errors on. It's possible to have 3 errors instead of just 1. But we can catch errors if we have more bits, right? Here, if only 1 error happens, we can catch that error because it's more likely that 1 error happens than 2 or 3 errors. So we've got a trade-off here, right? It's possible that more errors can happen just because there's more bits that have errors, but we catch some of those errors. And you can calculate the probability of this. So if you look at the probability of a logical error, so B misinterpreting the message, as a function of the physical error probability, this is the probability that each bit gets flipped on its own, then this is the performance. So D here is how many bits you encode. So D equals 1 means we do this naive thing where A just stores 0 as 0 and 1 as 1. D equals 3 means this thing here. Oh, sorry. D equals 1 is, oops, this slide where A just stores whatever she means. This is D equals 1. D equals 3 is this process where A uses 3 bits. D equals 9 would be A storing 0 as 000000000, 9 bits, so on and so forth. Right? So you can calculate the probability of misinterpreting the message, which is on the y-axis, for different numbers of bits. And you see here that the probability of misinterpreting the message gets lower and lower for a fixed physical error probability as you use more bits. Unless there's too many physical errors. If there's too many physical errors, then more bits just means more errors and you just lose track of everything. So you can actually prove that this thing, which is called a repetition code, has a threshold. More bits is always better as long as you have less than a 50% chance of each bit flipping. If each bit flips with a chance of 50% or more, then you don't gain anything from error correction. So as long as there's low enough error in the physical bits, this redundancy helps you remove some of those errors. It helps B interpret the message more accurately. So this leads to a little bit of vocabulary. Threshold is the error rate below which more bits or qubits is always better. And an error correction experiment is beyond break-even if logical bits perform better than the best physical qubit, or bit or qubit. So imagine that you had one really, really good bit, then you would just send your message with that. So this is actually a graph from Google Quantum AI from a few years ago, where this is the same thing. This is closely related to what I just showed you. So we have logical error probability on the y-axis, and there's something going on here, but the key point here is that lower is better, and the best physical qubit is this green one here. And they showed some results where using error correction, the collective of qubits that they were looking at performed better than the best physical qubit. So that's down here. Um, so that means that they're beyond break even. So so that's the idea of classical error correction. We use extra redundant bits in order to encode our message so that we can catch some of the errors and then correct them. So we know how to interpret messages that have a small number of errors. With too many errors, we're in trouble no matter what. But as long as the number of errors is low enough, you'll do better with this. All right, so I'm going to pause for a few questions here. Um, Let's see. So there was a question about the name of the YouTube channel. Perhaps, Ermal, if you want to type the answer to that one in the Q&A, you can give people the YouTube channel where things will be posted.
Yes, the YouTube channel will be available later throughout the week, and for that, it's easy to just find us if you just search for YouTube training NERSC. But I'll type it in the main thing as well.
Okay, great. Thank you. Uh, okay, so how is the threshold chosen? The threshold isn't chosen. So once you decide how you're doing the encoding, so in this case, once we decide that that A is going to store a 0 as some number of zeros and store a 1 as some number of ones, then the threshold falls out from that. And it also depends on exactly how your errors occur. So if certain errors are more likely than other errors, then that threshold will shift around a little bit. So once you've chosen the encoding, and if you know a bit about the noise, then you can calculate the threshold. It's not something that you choose. Um, what do I mean by best in best physical qubit? I mean according to various error probabilities. Roughly speaking, it's how often you measure the wrong answer when you measure your qubit, but there's a little bit more to it than that. Um, Error correction is used for channels in communication systems and also storage devices. Is this the same in quantum computers? Yes, it is. So I framed this as something as correcting error in storage, but you can think of storage as just a noisy channel. So absolutely, error correction is used for quantum channels as well. Why did I give the answer with 3 and not 2 or 4 bits? So I chose 3 because there's no ambiguous answers with an odd number of bits. So for example, if you used 2 bits and you got the message 0, 1, you would know that an error happened, but you wouldn't know which bit flipped. If you read 0, 1, did the first bit flip or did the second bit flip? Depending on which one, the answer how you'll interpret it would be different. And so 2-bit and 4-bit encodings are just a little bit more complicated. So 3 is a little bit cleaner. And we'll see that a little clearer in a moment. Let's see. Good. So what it implies, there's a question, what it implies is the decoding technique is the crux. So decoding is decoding technique is a very significant problem. We'll see a bit about decoding techniques in the second part of the talk, but there's actually a lot of things to worry about. It's not just decoding, it's also efficiently implementing a lot of things on your quantum computer in order to do the encoding and doing measurements and monitoring and processing the data, all of those sorts of things. There's a lot of challenges in quantum error correction, and we'll get to a bunch of those challenges as we go through this talk. All right. Let's see. Are there many ways to do encoding and decoding? Absolutely. So let's say classically, you can store a 0 as any message you want. You could store it as 01001101 and store a 1 as some other random bits. Or you could say I'm encoding 3 logical bits in 10 physical qubits. There's lots of different ways to do that. Absolutely. And decoding also depends on the way you do the encoding, and it depends on other constraints in your system as well. Okay, so somebody says redundant bits are used to decode errors classically. I can't wrap my mind around the idea that sending redundant qubits would act the same way. You're absolutely right. Sending redundant qubits in the same way here doesn't quite work. And we're going to see why that is in just a second. So you're absolutely correct, anonymous participant, that repetition codes aren't so great quantum mechanically. And we'll see that in just a minute. All right. There's a question here about how hardware dependent are quantum error correction methods. Good. So that's a complicated question. There are lots of different parts of quantum error correction, and different parts of them are hardware dependent, important to different parts of the hardware stack. So a quantum error correction approach developed for IQM hardware would be may or may not be applicable to one for IBM quantum processors, which is what's brought up in the question here. So among superconducting qubits, there's certain classes of error correction approaches that are kind of similar for in flavor, and the details are a bit different, though they can be conceptually different as well. If you start looking at something like trapped ion or neutral atom qubits, the error correction methods, the encodings that you would use are often quite different, and the constraints that you need are quite different, as well as the hardware that you need to do all of the classical computation in encoding, decoding, things like that. That also changes a bit. So there's a lot of different pieces of the stack, and different parts of it are different for different platforms, but even with the same type of qubits, let's say different error correction methods are optimized for different systems in general. So yeah, there's a lot of hardware dependence here. Let's see. Good. So somebody points out, if we are looking here, and 001 is okay because B will interpret this as a 0. If B receives 011, then what's most likely? B is going to say, let's say I got 011, then it's more likely that only one bit flipped. So which bit would probably have flipped? It would have been the first one. So let me actually see if I can get out a little pen for this. So if we put 011 here, then most likely this first bit flipped, because one bit flip is more likely than than 2-bit flips. And so probably we're going to interpret that as a 1. And so that would be incorrect. B would be wrong. But it takes 2 errors to make that happen. So it's 2 errors. Sorry, this is a little clunky on a laptop to annotate here. And this one is only 1 error. So in order for B to get the wrong message, 2 or 3 errors have to happen. And that's less likely than 0 or 1 error. Oops, sorry about that. But when I made the graph, when I made the graph here, I accounted for that. So I'm counting the probability just that among all possible messages, B gets the wrong, interprets A's message wrong. So, there is still some probability that B gets the wrong answer, but it's lower than if B didn't use redundant bits. Good. Is there an official name for this method? This is called the repetition code. What about 101? Same thing as 011. So if we receive 101, then most likely A had actually tried to send 111, and only one error had happened. So if B actually receives 101, B is going to get it wrong and assume that A had actually meant 1. So the idea here is that B doesn't know what A sent, but B is going to say, given what I've received, what's the most likely thing that A sent? And that would mean the message that took the fewest errors. So the most likely message would have been an error one there. Good. Are we going to talk about IQM research such as barbell codes, color codes, QLDPC, things like that? We'll talk a little bit about that at the end tomorrow. So the aim here is of this seminar is to do an introduction to quantum error correction rather than to focus on the newest and greatest error correction methods. But I'll talk a little bit about some of these things tomorrow. Good. How is the number of physical qubits and the number of logical qubits related? So that is a choice. We get to choose how many bits we do this in this encoding here. So for example, you could choose that the encoding goes from 1 bit on the left to 15 bits on the right, or you could choose 2. That's a choice. And the performance of the code, this is called a code. The performance of this code is going to depend on what you do. Now, obviously, as we just saw, having more physical bits for the same number of logical bits reduces your errors. But it costs you more. It costs extra bits. And so depending on what your limiting factor is, you want to change around the number of physical qubits and logical qubit per logical bit in order to optimize whatever it is that you're trying to optimize on your particular system. Is it likely that some errors occur during the encoding process? In quantum computing, yes, that is entirely possible, and we have to be careful about that. The probability of 110 and 101 is the same. I agree, and that's why for 110 and 101, the B would interpret them both the same way. So just to be clear here, if B received the message 101 or the message 011 or the message 110, they would interpret that as a 1. If they receive 001 or 010 or 101, or sorry, 100, they'll interpret that as a 0. So it's true that these are all equally likely, and these are all equally likely. And that's one of the reasons that they get interpreted the same way. Yeah, so exactly. It's just a majority vote. The decoding here is literally just a majority vote. Good. I see another question. In classical error correction, we talk about bit flips. In quantum, we have angles, phases, and amplitudes. Do we tackle them separately? Yes, we are going to get to that in just a second. So hang on to that thing about phase errors. Excellent. So with that, let me thank you for all the questions. A lot of really, really good questions here. So let me move along here. So what's different quantum mechanically? So let's repeat our experiment, but this time we're going to meet A and B again. This time, our stick figure, whose name is A, owns a quantum computer. And so A is going to store not a bit, but a qubit, and that's represented by a 0 with this ket notation. And they're going to stick the qubit into the quantum computer and store it and walk away. Now, somebody else, B, comes back and goes and tries to grab that qubit and says, let me find out what qubit A stored. So they don't know, and they want to find out. So let's try the same sort of thing. Imagine that if A wanted to store a 0, A actually stores one logical qubit in 3 physical qubits. Um, sorry, like this. So A stores 0 as 000, and A stores 1 as 111. Um, and so if A knows that what message they're storing, this is fine. There's no problem here with the no cloning theorem, but there are no cloning theorem issues. I mentioned this just because someone mentioned the no cloning theorem earlier. But this is a perfectly fine thing you can do. And you can do an encoding like this. So we carry on, and we get basically the same thing. If A wanted to store a 0, and one error happen and no errors happen, B receives 000. Let's say B measures the qubits and sees, I got 000. What did A store? It's a 0. Hooray! They got the right answer. Let's say B receives their qubits, measures them, and sees 001. Then they say, oh, most likely only one error happened, majority vote. So the answer is A meant to store 0. Hooray, B gets it right. And only if 3 errors happen does B receive 111 and get it wrong. Or if 2 errors happen, B will receive, majority vote will say that A meant to store a 1, and B will get it wrong. So with 2 or 3 errors, B is going to get it wrong. Everything's exactly the same as it was classically. So what's the problem here? Is there a problem here? So let me just point out that we've only been considering bit flip errors so far. And this is where an error where 0 turns into 1 or 1 turns into 0. So the thing is that we can store messages other than 0 and 1 in a quantum computer. That's not possible in a classical computer. So let's do a little thought experiment. What if A wants to store a slightly different message? A wants to store the superposition of 0 and 1. So a state with 50-50 chance of measuring 0 and measuring 1 with a plus sign here. Or maybe A wants to store a minus state, which is 0 minus 1. And these are opposite states on the block sphere, just as 0 and 1 are. So what that would mean in this encoding is that if A wants to store the plus state, they have to store 000 plus 111, which is a superposition of physical qubits to store one logical bit in superposition. Likewise, to store one logical bit in this superposition, they have to store let's say three physical qubits in this superposition. Now, this actually leads to several problems. So let's see what those problems are. So the first problem is that there's new types of errors. So if there's no error, and A decides to store this plus state, if B receives this plus state, everything's fine. But what happens if there's this error on a single qubit, right? 0 goes to 0, but 1 goes to -1, right? Now, there's no such thing for classical bits as a phase error like this. This is called a phase error when the state 1 picks up a minus sign and the state 0 does not. That just doesn't exist classically. But what does that do to the state that A stored? What it does is it turns it into this state with a minus sign on the 111 thing. And so what that means is that if only one qubit has an error, we got a logical error. We flipped from the state plus over here to the state, the logical state plus to the logical state minus by only doing one qubit's worth of error on one physical qubit. So that was the same thing that happened earlier when we didn't do any error correction, right? If we just had 0 is 0, 1 is 1, one error makes us completely misinterpret the message, and we have no way to know. So so an error on just one qubit causes a logical error, which is what we were trying to avoid. Our error correction was supposed to help with this situation, and it didn't. And this type of error, as I mentioned, is called a phase error. Let's see. So a couple of questions. What if it's 110? Then you also interpret 1 right. Yes, that's correct. It's just a majority vote. By 001, I don't mean so this person is asking, do I mean several runs of individual qubits, or are they all sent together? So this would be all of the qubits sent together. And the question asker asks further, if they're sent together, could that influence the qubits? Yes, that is possible. So the fact that you have multiple qubits near each other, they can influence each other, and that could introduce noise to the system. That's also something that can happen classically in principle as well. But we do have to be very careful about that sort of thing in quantum, and I'll address that a little bit later. How can we determine the expected number of errors introduced after encoding so that we can select an appropriate repetition factor for error correction? Good. That's a question about hardware. So you have to measure the physical hardware that you have and see what your error rates actually look like. And if you do well-controlled circuits so that you know what your errors are and how often they occur, then you can try to figure out what a good encoding would look like for your particular system. More often, you measure that and just adjust your decoding appropriately. You usually tend to use in certain situations, which I'm not going to really get into, you change the number of qubits, but like let's just say to 0th order, you fix the number of repetition of extra qubits you would introduce, and then adjust your decoding so that you know based on the way that the error, what you know about how errors occur in your system. Good. Let's see. There's another question here. Is it better in quantum systems to send or store more qubits in the first message, or to send shorter messages and only retransmit if an error is detected? Good. So in general, if you're just retransmitting every time an error is detected, that in quantum systems, that's going to introduce an exponential overhead in the number of messages that you have to send. And exponentials are bad. So you can do that, but it does not. But that's going to cost you a lot of an exponential overhead. Furthermore, you can't always send shorter messages. If, for example, you entangle a large number of qubits, you can't take an entangled state and decompose it into many shorter messages. So it's just not always possible to send shorter messages at all, just because all of your qubits may be correlated in some very complex way. So yeah, that's a very good question. Yes, let's see. Are we going to touch on the principle of anomaly detection? So I'm going to talk after the break about how we detect errors in a QEC situation. Yes. Okay. So the other thing that's an issue here is how do we actually check for errors? So in order to actually, let's say A stored this state, this plus state. Now we have to measure something to check if there was an error. The problem is that if B measures one of these qubits, the state changes. Measurement in quantum mechanics causes the state to change. Even if errors don't occur, if B measures one of the qubits, they'll find out that they get 0 or 3 zeros 50% of the time, and 1 50% of the time, and then the state is going to change to 0 0 0 or 1 1 1. And so the state that A had stored gets lost after a measurement. So what did A send? Plus, minus? That's getting zeros 50% of the time, or getting ones 50% of the time, would give you the same, would happen whether A sends a plus state or A sends a minus state. Furthermore, maybe A is sending 0 half the time and 1 half the time. You have no way to tell the difference in this situation. So you can't even tell what you lost the state that A sent just by checking for errors. So a quantum code has to get around these problems. It needs to do a sequence of measurements so that, first of all, if we make a measurement reading 1, some error happened. If we have all of the measurements reading 0, no error happened, most likely. And the measurements don't distinguish between good logical states. And the reason we need this is that we don't want a measurement to collapse logical plus into 0 or 1, right? If we just measure a qubit, one of the data qubits here, then it's going to cause this to collapse into a state that was different from what we wanted. And so whatever measurement procedure we do, hint ancilla qubits will be involved, it had better not collapse this superposition. So it better not be able to tell the difference between 0, 0, 0 and 1, 1, 1 when we're checking for whether or not there's an error at all. So we're trying to check if there's an error. And we don't want that to mess up our superposition. So the summary here is that QEC has two key problems that are not present for classical error correction. One is that we have to detect and correct both bit flip and phase errors, this extra type of error. And secondly, measurements, disturb quantum states. We have to avoid collapsing logical superpositions when checking for errors. Good. So I have one more topic before the break, which will this will probably take me about 10-15 minutes to get through. So I don't see a lot of open questions right now. Yes, there's a question, when we do a measurement, will we lose the superposition state? Yes, that is correct. Let's see. Okay. So let's talk a little bit about the road to fault-tolerant quantum computing. So we're going to zoom out now. I've motivated what error correction is and why it needs to be different for quantum computers. We'll get to what it is in quantum computing after the break, but let's see where the field is headed first. So in general, there's a sequence of experiments that you can run that give you information about how well you can do quantum error correction. And these kind of all have to be done in order to develop a fault-tolerant quantum computer. So, for example, the experiment that you'll be doing hands-on tomorrow is called a quantum memory experiment. And it asks the basic question is how long can you store a logical qubit before losing the information? How good are you at encoding and then your logical qubit into physical qubits, and then keeping them keeping errors from happening. Now, there's a bunch of other things as well. So quantum stability talks about moving information in a logical qubit. I'm not going to describe any of these in detail, but that's kind of giving you the general gist of what this experiment does. There's lattice surgery experiments, which ask about how you can implement simple quantum gates on your logical qubits, specifically on your logical qubits. Then there's two things about which work up to implementing complex quantum gates. Now, I'm using simple and complex to get rid of some technicalities here. I'm happy to talk about this if people are interested, but let me come back to that later. But these two experiments on T-state cultivation and T-gates are basically about how well you can prepare and implement complex quantum gates on your logical qubits. So this is all about logical qubits. And all of these experiments need to be understood, and they need to be done well in order to have a good full-scale quantum computer. So these have to be done. These also have to be done with what's called real-time decoding to get a practical fault-tolerant quantum computer. So there's two things. We need to do real-time decoding, and I'll explain what that is in a second. But you also have to do these very well. You have to answer the question, I can store a logical qubit for a long time. And you have to be able to answer the question, I can implement simple quantum gates very well. Right? So all of these experiments are a question of degree. It's how well can you do this experiment. So we'll dig into the quantum memory experiment tomorrow, but let me talk a little bit about real-time decoding, because this is one of the biggest stumbling blocks in actually building a quantum computer. So there's two different things, types of decoding. So we talked about decoding, right? It's taking the message you receive and asking, was there an error? And how do I make sure that I got the right message in the end when I interpret my message? So there's offline and real-time or online decoding, but real-time is probably a better way to think about it. So the way to think about offline decoding is that you do some measurements down here that you can think of as checking for errors, and then you do an operation on your qubits, and then you keep checking for errors, and you do an operation, and then you keep going, and at the end, you say, okay, well, I had a pile of errors that looked like so. Maybe I had an error here, and no error here, and an error here, and so on and so forth. You look at the end result, you do some correction on your classical computer, and then you get your answer. So there's you run your quantum program, measuring all the way, doing specialized measurements all the way, and then you do some classical computation at the end. And this is great. This is straightforward enough. But there's another possibility. Oh, and I should just mention, each of these things that I boxed here is what's called an error correction cycle. It's a sequence of measurements that says, do I have an error? Do I have an error? Do I have an error? Now, on real-time decoding is different. Real-time decoding says, I'm going to do some check for errors, and then I'm going to do my operation on my qubits, and I'm going to check for errors again. And then I'm going to process that and say, okay, there's a pile of errors which may have happened here. Let me fix those errors quantum mechanically. So I actually introduce a new quantum process in the circuit, which is classically controlled. It depends on the results of all of these prior measurements. So there's actually some missing wires here that these other measurements come in here as well. So all of these different measurements influence the correction that you do. And you do that before proceeding with the rest of the quantum circuit. So before moving to your next operation, you do that correction. And then you say, check for errors. Do my next operation. Check for errors. Correct. Carry on. So in the middle of the quantum circuit, you have feedback mechanisms that change your qubits. Now, why is so offline decoding seems simpler, right? You just do a bunch of measurements as you go, you pile up information, and then at the end, you say, okay, I've got my readout information, let me fix everything. Real-time decoding requires you to process information in the middle and mess with your quantum circuit in the middle of execution. So why would we want to do real-time decoding? Real-time decoding is very important for the following reason. So this is a circuit that the idea of this circuit, let me walk through what's happening here. We take some logical bit, and our goal is to implement a special type of operation, which in this case happens to be what's called a T-gate on this logical qubit. Now, it turns out that in order to do this, the most effective way to do this for a logical bit is something kind of complicated. You prepare a special state called a T-state. This is a logical state. It's, again, many physical qubits, not just a single one. And then you run this circuit in order to take this special physical state and turn it into a T-gate acting on your input state. But this circuit requires doing a measurement of this logical qubit down here, and then taking the result of that measurement and deciding what you're going to do to your input. So the way to think of this is this one's an input, and this is a resource. And so you're going to manipulate the input qubit depending on how you measure the resource. And if your measurement on the resource qubit is wrong, you're going to do completely the wrong gate here. So you had better make sure that whatever you measured for the resource qubit is actually correct, that no errors happened there before doing the correction. So in the time from measuring your resource state until you apply something to the input state, you have to do error correction. That's why we absolutely have to do this. In order to do all error operations on logical qubits, real-time decoding is required. Why this is not obvious, but it is true. And so that means we have to process the measurement, decode, and apply a correction within a fairly short time, right? We take this measurement outcome, we check, we decode, we figure out what we were supposed to get, and apply the correction. So how short is that time? So there's a fundamental limitation on how short that time has to be. You have to check for errors often enough that your physical qubits don't decohere, which basically means lose their quantumness. They forget that they're all the quantum information. And this is limited by what's called the T1 time for the qubits, which is for superconducting qubits, typically 10 to 100%. For certain other modalities, it can be longer. For certain other modalities, it can be shorter. And so that's an absolute limitation. So you might say, okay, well then, so you say, okay, I have to measure faster than that. So 10 to 100 microseconds is pretty quick. And you also need to decode faster than you collect measurements. You don't want your data to pile up before you decode it, right? If as you're doing the decoding, more information than you're processing comes in, then you got a problem, right? So, there's also this question about how fast you collect the measurements. You have to do the measurements fast enough that you don't forget the physical, that you don't decohere, and you have to decode those measurements even faster than you collect them, right? So why not just say, let's take the longest T1 time I possibly can get and do QEC with that, right? If the limitation here is I have to do something faster than T1, just get a longer T1 time, maybe a different modality. There's a practical limitation here, which is that spending time doing QEC is time spent not doing useful gates. It's not running your algorithm. It's just checking and correcting errors, right? So if you spend 20 seconds doing QEC, that's just time that you wish you could have been spending algorithms, right? So superconducting qubits here actually have 2-qubit gate times, which are tens of nanoseconds. That's tens of nanoseconds, not 10 seconds of nanoseconds, tens of nanoseconds, so 10, 20 nanoseconds. And that's the fastest of all modalities. So even though there are modalities that have longer T1 times than superconducting qubits are also really, really fast. And so you want to use that gate speed to do your algorithm fast. And so, yeah, you want to do your QEC really fast. So there's this trade-off between doing your actual computations fast because we want to go fast and having a big data problem to where you're piling up a bunch of information from your QEC circuit and that you have to process over time. I'm seeing a lot of questions pile up. Let me check a couple of these. Let's see. The quantum memory experiment is seeing how long the logical qubit survives based on the physical qubits. The question is the quantum memory experiment for physical qubits or logical qubits? So it's seeing how long you can protect a logical qubit. And real-time decoding the question is it happening after each operation or after a prior set number of dynamics? So real-time decoding is actually basically happening all the time. So you do a certain number of you do some decoding, you do an operation. You do some decoding, you do an operation. And in fact, there's even a sense in which certain operations require decoding in the middle of the operation. So it's not as cut and dried as are they happening after each operation. There's just kind of constant decoding going on, even in the middle of operations. Consideration comparing offline decoding with post-selection and real-time decoding with feed-forward operations. Good. So offline decoding with post-selection means that you go through the circuit and you say, did an error happen? If an error happened, throw out that shot. Did an error happen? If so, throw out that shot. So that means you're throwing out a very large number of shots. And in fact, you end up throwing out exponentially many shots. In principle, with real-time decoding, you don't have to throw out any shots. You just have to do a bunch of operations really fast and really efficiently. So there's a trade-off to happen here, but post-selection is guaranteed to be an exponential cost. And a number of shots means exponential time, an exponential amount of time. So in general, for small numbers of qubits, post-selection is fine. When you really get to a large number of qubits, it's not going to work. You're going to need real-time decoding. Let's see. So when we say that QPUs operate in nanosecond latency, are we talking about T1 times? No. So nanosecond latency is, we're talking about gate times here. So it's single operations on your qubits. And this is particularly superconducting QPUs operate with nanosecond latency. When you're looking at other modalities, they are in general going to be slower than that. T1 time is just a limit on how fast you have to do error correction fast enough that you don't lose quantumness. Don't each of the measurements affect the state of the system? They do. And so we'll talk after the break about how we do that in such a way using even some extra qubits so that we don't mess up the state of the encoded logical qubit. So yes, there's a question, is the measurement done on ancilla qubits for the logical qubits? Yes, that's correct. How many logical qubits you need is somebody asked if gave a scaling there. In general, I'll show the scaling here for the surface code tomorrow, actually. Yeah, it's polynomial in n qubits. As opposed to post-selection, which is exponential in the number of qubits. Does the number of resource logical qubits scale linearly with the number of logical qubits? Right. So the number of resource logical qubits you need actually depends on a lot of things. It depends on how fast you want to be doing specific types of operations. So yeah, it scales with the number of logical qubits. I think you'd have to talk about a particular application, whether you wanted to say that's linear scaling or some other type of scaling. In offline decoding, errors in the system may vary or be constant. I don't quite understand the question. Sorry about that. What about dynamical codes where the role of data and ancilla qubits keeps interchanging? So that is one complex thing that you can do in this situation. Yes. But that ends up changing. Yeah, that just is a matter of the practical implementation. How do errors lead to decoherence in qubits? Aren't they just errors that change the bit or the phase? So there are more errors that could happen beyond bit and phase errors. But it turns out that with QEC schemes, you actually only need to worry about bit or phase flip errors. So there are other types of errors that can occur as well. And you mostly only need to worry about those sorts of errors. I'll talk about some of the other types of errors that can happen as well. Let's see. Is there any hope for quantum error correction with no-go theorems like Easton nil? Absolutely. People are working on quantum error correction right now. People are implementing all of these quantum error correction experiments. There's a lot of things that can go on here. How will we make sure that the resource state is measured correctly? That is has to be part of your quantum error correction scheme. So you have to be careful that, and we'll get to this in just a second. I'll talk a little bit about fault tolerance later today. Let's see. In real-time decoding, how does T state related to the input state? So, okay. So what I showed here is not actually real-time decoding itself. What I'm saying is that in order to implement specific operations on logical qubits, you need to have a resource state, and you need to do feed forward of your measurement to the inputs of a measurement on a resource state to the input state. So real-time decoding is required in order to do operations on your input, specific types of operations on your input state. Those operations not only require real-time decoding, but they also require these input states to be prepared. So measuring the T-state doesn't help with error correction. Error correction helps make sure we do our T-gates appropriately. A T-state, the question is a T-state a so-called magic state? Yes, a T-state is a form of magic state. There are many magic states. Basically, a magic state is one that's not preparable efficiently with not preparable with Clifford circuits. Good. Are resource qubits and physical qubits the same? So in this situation, this L here means that these are logical qubits. So each of these things is actually several physical qubits. So this is all at the logical level. They're not physical qubits. So in order to do a logical T-gate, so an operation on a logical gate, that means that we need to do this measurement on this extra logical qubit. What is a Clifford circuit? A Clifford circuit is a special type of circuit which is classically simulable efficiently. It's one that takes the poly group to itself. So real-time decoding is only needed for non-Clifford gates. That's correct. In principle, offline decoding is fine for Clifford gates. Let's see. When we measure offline mode, we need to fix and then measure again, so we get another error in the system. So no, the goal of QEC is that you should be robust to measurement errors that happen in the QEC process, and we'll get to that in a second. What is the measurement block? The measurement is literally just measuring the qubit. So this is a logical qubit. The question is that logical qubit a 0 or a 1? We do a measurement, and exactly what that means physically depends on the system. Okay. All right, I'm going to keep going for a little bit here. All right. So one other thing to point out is this is something that's been coming up in a lot of the questions. So error correction versus fault tolerance. So and we saw earlier that, for example, that repetition code, it was able to fix one error, but it couldn't fix two. It turns out that in quantum systems, if you have an error that happens before an operation, after that operation, it looks like an error happened on more than one qubit. So we started with one error, and after the operation, we ended up with two errors. This is really bad because we thought that we were able to correct a single error, but then we did some operations to the qubit instead of just waiting. And now we have more errors and we lost correction there, right? We could only correct one error, not two, for example. So that's something we have to be aware of when we're designing our error correction circuit. Also, as has kind of been pointed out, perfect quantum error correction would say, okay, I took an error, a state that might have an error, I do perfect QEC, and I get a correct state. But if your QEC is itself imperfect, you might start with one state with an error and end up with another state with an error, maybe a different error, but something else. And so what we need to do is design our quantum error correction process in such a way that avoids these two problems. And that's what we mean by fault tolerance. So when we say that we're doing fault tolerance, it means that we avoid pileup of errors from in the way on top, and that our error correction doesn't introduce more errors than it corrects. That would be really bad. Good. So that's all of the content that I have right here. I'm going to answer the last few questions in the next couple of minutes, and then we'll take a 15-minute break. So let's see. Other questions here. Does the type of coupling between qubits affect the performance of QEC? In print, yes, absolutely. So depending on how the qubits are coupled, this can actually change the way that the noise behaves, and you need to adjust your QEC in order to compensate for that noise. Let's see. So can you tell about the best simulation tools for quantum circuits? So there are a number of simulators out there. There's the air simulator that I know of off the top of my head. And if you're looking at quantum error correction, if you want to simulate noisy QEC circuits, STIM is kind of one of the industry standards there. But there are other ways to do this as well. Let's see. I will try to get to some of the other questions. There's a question about weak measurement. I think I'm going to have to come back to that one if we have time at the end. So sorry about that. I'm going to have to come back there. Having many readout shots and having quantum non-destruction at the same time is confusing for me. How does many readout shots happen without collapse of the wave function? So we'll see how that happens after the break. The goal is actually just to use a few extra qubits so that you collapse specific qubits without collapsing the ones that are encoding your message. And we'll see how that comes in just after the break. Good. If we start with an entangled state, can it be preserved after the QEC process? Yes, and that is actually one of the main points of doing QEC, is that we want to preserve entanglement. Good. So if you have other questions sitting open, it's either because it's something that I want to answer offline, or I haven't quite understood your question. So I will try to type a few answers to some of these questions during the break and see if we can if I can get some clarification for you folks. So yeah, now is probably a good time to take about a 15-minute break. Come back at 10 minutes to the hour in your favorite time zone.
Perfect. Yeah, that will take a 15 minutes. Thank you for the great overview, Danny.
All right, shall we get started again?
Yep, I think we're good to restart. Um, yep, please go ahead.
All right, sounds good. All right, so like I said before the break, we've only talked about classical codes and a pretty bad quantum code, the repetition code. So we'll do a little bit more on simple quantum codes now, and we'll dig into a bit of the decoding problem as well. So we're going to take one step deeper into the quantum bit. So the first question is, how do we actually check for errors in QEC? Then we'll talk about how we detect both bit and phase flip errors. We'll talk a bit about why decoding is hard, and then we'll finish by talking about a brief overview of different types of decoders. So I think these first two questions in particular have come up a lot in the discussion, so hopefully I'll be able to clarify that. So before the break, we saw that we wanted to do the following. So we want to do a sequence of measurements so that a measurement reading 1 means that some error happened. 2, if all the measurements are 0, no error happened, most likely, but not for certain. And 3, measurements don't distinguish between logical states, meaning that the measurements don't collapse the wave function. Let's say we have a logical plus into zeros or ones. So how do we actually, we need to do these measurements that check if an error happened. So how do we do that? So the most standard, let's go back to our repetition code. So now to make things super clear, when I talk about a logical qubit, so the message that A is sending, I'm going to put an L here to make sure that we're talking about a logical qubit. And I'm going to leave off any subscripts when I'm talking about physical qubits. So let's notice something. If there's no error, notice something very interesting. If there's no error, all of the qubits are the same. Okay, why is that interesting, Danny? That's just what we decided. But let's see something else. We can sort. Imagine, so what is the most likely type of error to have happen? Most likely, one error happens. So it's much more likely than 2 or 3 errors. So suppose that the most likely error was that the first qubit had a bit flip. Well, what states are those? 1, 0, 0 and 0, 1, 1. Those are the states that we get from having one error on the first qubit, right? So if the only error is the first qubit flipped. So notice that whether we started with all zeros or all ones and then had the error, in either case, the first two qubits are different, and the second and third qubits are the same, right? If the first qubit flipped, no matter what we started with, the first two qubits are different, and the second and third are the same. If the second qubit flipped, no matter what we started with, the first two qubits are different, and the second two qubits are different. And if the third qubit flipped, then no matter which one we started with, the first two are the same, and the last two are different. So the key point here that I want to emphasize is that whether the first two qubits are different and the same, and whether the last two qubits are different and the same, is enough to tell you what error happened, most likely, regardless of what state we started with, right? So what that tells us then is now we have what's called a decoder. And this decoder is a very simple decoder. It's a table. It says, let's make some readings. We're going to check whether qubits 1 and 2 are the same or different. And we're going to check whether qubits 2 and 3 are the same or different. And let's call same 0 and different 1. So if our measurement, are the first two qubits the same, gives us 0, and our measurement, are the last two qubits the same, gives us 0, then we say most likely no error happened. And we do nothing. There's no error to fix. If the first two qubits give us 1, if the first two qubits are different, which we're going to call 1, and if the last two qubits are the same, which we're going to call 0, then that means that qubit 1 flipped. And so we fixed the error by flipping qubit 1. Same thing for these other pieces here. Now, the key point here is the zeros and ones in this table are not the qubit. They're just representing whether qubits 1 and 2 are the same or different. So it's partial information about the qubits. It's not saying what is qubit 1 and what is qubit 2. It's just asking, are qubits 1 and 2 the same or different? And that's the measurement that we want to do. Because if we ask, are qubits 1 and 2 the same or different, it will never change the errors, these states. It can't take us, for example, between any of these states. It's not going to manipulate that state if we do the measurement right. So we have to be careful, but our aim is to avoid that measurement. And the key point is that no matter which state you started with, you can figure out which error happened without figuring out which state you started with. All you need to know is qubits 1 and 2 different, or qubits 2 and or the same, qubits 2 and 3 different or the same. So what are we doing? These are called syndromes. So syndromes are measurements of partial information that help you identify the most likely errors, and they don't destroy the encoded state because the answer is the same no matter which state was sent. So for the 3-bit repetition code, we measure 2 syndromes. Are the first 2 qubits the same or different? That's one syndrome. It's a bit of information. And we also ask, are the last 2 qubits the same or different? It's another bit of information. So with these 2 bits of information, we figure out what the error was and how to correct it. And this thing about not destroying the encoded state, the key point here is that if we encoded a superposition of these states and the first qubit flipped, then we would end up with a superposition of these states. So the error that happens doesn't disturb the superposition, it just changes which states are superposed. So as long as we can do this measurement without collapsing the wave function, then we can correct it and go back to the original state, because we know which bit flipped without collapsing the superposition. So I do want to mention that syndromes actually define a code. So given a set of syndrome measurements, we can define a code by listing, actually a basis of, all of the states which would have no errors. That is, the syndromes would all be 0. So for example, I'm going to pose a question to the audience. List all of the 3 qubit states where the first 2 qubits are the same and the last 2 qubits are the same. I'm going to let everyone think about that for a few minutes, or for a minute or two.
Who's
You
this?
can post your answer to chat.
Are you done?
Please don't unmute yourself. You can post the answer into chat. If you want to answer the question, please feel free. Just do it in chat, please. Good. So I saw somebody answer in chat the answer 001. So 001 has the first 2 qubits the same, but not the last 2 qubits. So we want both of these things to be true. The first two and the last two are the same. Right, so now I'm seeing the right answer in chat. The answer is that the only states where the first two are the same and the last two are the same are 0, 0, 0 and 1, 1, 1, and superpositions thereof. So it's not just these states, it's also superpositions of them. And so what that means is that just by saying what syndromes we're measuring, we've decided which states we're using in the encoding. So here's our 0 logical state, and here's our 1 logical state. Now, the astute among you may notice that there's not that we actually could have swapped that. We could have called 1, 1, 1 the 0 logical state, and we could have called 0, 0, 0 the 1 logical state. So that so there is some symmetry here, and so when we're using the syndromes to define the code, there is a little bit of ambiguity there. So we have to make a decision on which of the states we're going to call 0 and which of them we're going to call 1. But that's okay. The point is that the syndromes uniquely define the set of states that are going to be our 0 and 1. We just have to decide which one we're going to name which, and that's just a naming statement. So I'm going to come back to that in a little bit. So we've seen syndromes. So now the question is, how do we experimentally measure a syndrome? So our goal is to measure 0 if qubits 1 and 2 are the same, and we're going to measure 1 if they're different. But our goal is we have a constraint, which is that we can't measure the data qubits that are actually in the code, right? The 0, 0, 0 and the 1, 1, 1, because that collapses superpositions. We don't want to measure the qubits that we were using. So what we do instead is we use extra ancilla qubits. And the ancilla qubits I've listed as A here, and we have one of them per syndrome. So the idea is that these 3 qubits on the bottom, these data qubits, 1, 2, and 3, are going to encode the logical state. They're going to encode the 0, 0, 0 or the 1, 1, 1 that we start with. And these A1 and A2 are used as extra tools to measure the syndromes so that we can measure something without collapsing the data qubit superposition. So let's see how we can do this. So our ancilla is let's focus in on our first measurement. So we're just down to the 3 qubits over here. So our ancilla is going to start in the state 0. Here's a trick. For each of data qubits 1 and 2, we want to flip A1 if the data qubit is 1. Then, after doing that, measure A1. So take a minute and convince yourself that this actually does what we want. For each of the data qubits, we flip A1 if that data qubit is 1. And remember, our goal was to measure 0, our ancilla qubit to be 0 if qubits 1 and 2 are the same, and measure our ancilla qubit to be 1 if they're different. So I'll give everyone a moment to think about that. Convince yourself that that's right. Check the Q&A. Good. I see an excellent question, by the way, here, which is, can we say 0, 0, 0? Let me actually write this out. 0, 0, 0 plus I times 1, 1, 1. Can we say that this is equal to 0, L and 0, 0, 0 minus I, 1, 1, 1 equals 1 logical? Yes, you can make that state. You can make that decision if you want, as long as you choose any 2 orthogonal states that are superpositions of the logical states. That's a perfectly fine way to define the code, but we're not going to right now. Good. I also see the question is, are ancillary qubits similar to parity bits in classical communication? Yes, they are. They're very similar. Good. So I hope you've all convinced yourself. So the idea here is imagine that data qubits is one and 2 are both 0. Then there's no flip of ancilla 1. And so ancilla 1 is in 0. If they're both 1s, ancilla flip 1 gets flipped twice. And so it goes 0, 1, 1, 0. And that tells us that if both D1 and D2 are 1, then A1 is still 0. So if D1 and D2 are the same, there's an even number of flips, and A1 stays 0. If D1 and D2 are different, then there's an odd number of flips, and A1 ends up being 1. So the question now is, can you create a quantum circuit that does this without modifying or measuring D1 or D2? And that's the key. If we can create a quantum circuit that does this flipping process without modifying D1 or D2 or measuring them, then we've measured the syndrome. So I'll give everyone a couple of moments to think about that. I'll give you the answer at the end, but you should try to construct this circuit on your own. Good. So I'm seeing the core idea of the answer coming up. It's C-naught gates. So the idea here is that we want to do a control on data 1, target A1. That is what flips A1 if D1 is 1. But it doesn't modify D1. Then we do that for both of the qubits, and then we measure the ancilla. The key point here is that this entangles D1, D2, and A1, but then the measurement will disentangle them, and it will give us the answer we want. You can go through very carefully and check for yourself that this doesn't collapse any superpositions. If you prepare the 000 plus 111 state, after measurement, you will still get the 000 plus 111 state. So I see a question, would this entanglement of A1 with D1 and D2 lead to a mixed reduced state for D1 and D2 later? So if we didn't measure A1, then the answer to that question is yes. But because we're measuring A1, we will end up knowing the value of A1, and that will not give us a mixed reduced state for D1 and D2. Oh, sorry, let me think about that actually. Yeah, okay, sorry. So let me clarify that slightly. So if there's an error, this came up a little bit earlier. If there's an error that is not just a bit flip error, if it's something that's like let's say a square root of a bit flip, then the measurement of the ancilla would actually collapse you into a state that is either a bit flipped or not. And so oddly enough, measuring the ancilla gets rid of the mixed reduced states that you could get with kind of analog errors. So I didn't have a slide on this, but maybe I should add one in the future. This process of measuring the ancillas actually kind of turns analog errors into discrete ones. And that's exactly by this process of starting from a mixed reduced state and then turning it and then doing a measurement. Good question. What if A1 is measured wrong because of error? Then you're out of luck. Then you've got the wrong correction. Ideally, your decoder would be able to address this. but this simple decoder can't handle that situation. That's one of the reasons we don't use the repetition code. It can't handle measurement errors. Question, if you average over all A1 outcomes, we're just doing this experiment once. So the idea is if you just measure A1, you either find out an error happened this time or not, right? The whole point with errors is if you do this process many times, you're not just averaging over A1 outcomes, you're averaging over the errors as well. So there would be a whole bunch of different errors in different situations. So it doesn't work to average over A1 outcomes. You want to find out, did an error happen this time that I ran the circuit? Not on average, did an error happen or not? Good. So these sorts of tricks are exactly how we measure syndromes without collapsing superpositions, logical superpositions. Our whole goal is to basically non-destructively measure these parity checks. These are data qubits 1 and 2 the same or different? And we can do this using this C0 type of trick. All right, but the repetition code, we said, has a problem, which is that it can't detect bit flip errors. Bit flips just lead to logical errors. So that's no good. And so we need a different code that can detect both phase and bit flip errors. And that's why the repetition code's not really a very quantum code. So here's a simple example of a code. It's called the 422 code. And the reason is the 4 means that there's 4 physical qubits, data qubits 1, 2, 3, and 4. It's got 2 logical qubits. So we have 2 logical qubits in our logical states. And this 2 is something called the code distance. And we're going to see the code distance in a lot more detail tomorrow. It basically tells you how easy it is to make to flip the logical state of one of the qubits, one of the logical qubits. But that's just some notation. So this code says we're going to encode these logical states of 2 qubits, so 0, 0, 1, 0, 0, 1, and 1, 1, into these somewhat funny superpositions of physical qubits. So let's unpack that a little bit. Because so far I've just handed you random superpositions that are my encoding. Let's see if we can understand the structure a little bit. First, how do we do a bit flip on the first logical qubit? So the idea here is we want to turn 0, 0 into 1, 0, or 0, 1 into 1, 1, because we're flipping the first qubit, but leaving the second logical qubit the same. So what do we have to do to the physical qubits to flip these logical qubits? I'll let you all think about that for a little bit. Feel free to share your answers in chat this time. Oops. Good. So I'm seeing the right answer come up. We need to flip the second and fourth physical qubits, right? Because the difference between these first 2 lines on the physical side is that this second qubit and this fourth qubit are different between these 2 lines, whereas the first and the third are the same. And you can check that that's the same thing on the next one. So flip physical qubits 1 and 3. Sorry, I need to check something real quick. Oops, my apologies. Let me fix this. I'm having a very small computer issue, so I'm going to leave up the next quiz question, and I will be back in under a minute. My apologies.
No worries.
Good, and we're back. Sorry about that. Let me get the PowerPoint up again. Good. All right. So now the question is, how do we flip the second logical qubit? So I'll let people digest that for a moment with the slide actually up. Good. So good. So now to flip the second logical bit, we want to turn 0, 0 into 0, 1 logical and 1, 0 into 1, 1 logical. So if we compare, say, this state and this state, we can get to that by flipping the third and fourth bits. And same thing here to here. Now, if you're, for those of you who are paying super close attention, you'll notice that you can flip the third and fourth qubits, but you could also flip qubits 1 and 2. And the reason is that if we flip qubits 1 and 2, that's going to turn all zeros into 1, 1, 0, 0. And it's going to turn all ones into 0, 0, 1, 1. So there's actually two different ways to do this. You could flip qubits 1 and 2, or you could flip qubits 3 and 4. So there's a funny redundancy in this code. But that's kind of just a quirk of this particular code. Okay, good. So what we've seen is that by flipping either qubits 1 and 3 or qubits 1 and 2, up to this redundancy thing, we can flip the logical qubits. So, but this is just to get some intuition for this code. The important thing about this code is that it can detect both bit flip and phase flip errors. So let's see how that happens. So let's start with the part that's more familiar. We want to detect if one physical bit flip error has happened. So let's think about that for a second. What does that mean? So if a physical bit flip happens, let's say it's in the first qubit, then under that error, this first thing is going to turn into 1, 0, 0, 0 plus 0, 1, 1, 1, right? And this second one, if we flip the first physical bit because there was an error, we end up with 1, 1, 0, 1 plus 0, 0, 1, 0, and so on and so forth. So this takes some thought, but I encourage you all to think about what do we want to measure to detect if that happened without telling which logical state we were in. Seems like this one's a trickier question. So let's compare. I see a. Oh, good. I'm seeing some good answers here now. So okay, good. So I'm seeing the right answer. We want A1 to be 1 if there's an error. Somebody said something about comparing the first two, middle two, and last two. So let's actually take a look at that. So if let's say we compare the last two qubits, then this first one, we wouldn't detect that error, right? Because if there's a single, oh my goodness, if only the first qubit flipped, then in our error state here, the last two are the same. But if we started with 1, 0, in our error state, the last two would be different. So just measuring the last two is not enough. But somebody also made a suggestion of doing 3 different measurements, comparing the first two, the middle two, and the last two. There's something simpler, which is what some other folks were saying, which is just count the parity of zeros or of ones, right? All of these logical states have an even number of ones, right? Here it's 0, 4, 2, 2, 2, 2, 2, 2, right? So if we count whether an even or an odd, so if there's a bit flip, then it turns out that we immediately know that, and I typoed this slide. Let me fix that typo, because that's a very important typo that will be very confusing if it comes up wrong. There we go. Fix that. Okay. So if we do, we always start with an even number of ones. And so what we want to do is we want to check if there was an odd number of ones, because that would tell us that a single error had happened. Now, it turns out that in this particular code, you can't tell which physical qubit got flipped. There's just not enough information available. And it also, so this means you can't actually correct the error, but that's a technical detail here. I'm building up to a different point here, because this is a very, very oversimplified code. So the aim here is that A1 should be 1 if an odd number of data qubits are in the state 1, because that means most likely 1 bit was flipped. For those of you familiar with poly operators, that means we should be measuring the tensor product of all 4 poly z's. So I'm going to add this in for the folks who are getting a little bit, who are like, wait, but you're just measuring an operator. Yes, you're measuring an operator. And the operator you're measuring is ZZZZ. If you don't know what that is, don't worry about it. So we can detect a bit flip error, and that's by checking if there's an odd or an even number of data qubits in the 1 state. But now the question is, what should we detect? What should we measure to detect if one physical phase flip error has happened? Now, this is not obvious from what's happened here. But what would happen? But let's see what would happen if we had a phase error. If we had a phase error, let's say on the 4th qubit, let's say this one, then this thing would turn to a minus sign. This thing would pick up a minus sign, because there's a 1 in the 4th slot. This would pick up a minus sign, because there's a 1 in the 4th slot. And this thing would pick up a minus sign, because there's a 1 in the 4th slot. So the minus signs that I've drawn in here give us the error state for if there's an error on, let's say, the 4th qubit, a phase error on the 4th qubit. So can anyone identify what we should measure in order to detect that error had happened? I see CZ gates. That's a good That's a good guess. You might already know it, but if it's just a guess, that's an excellent guess. I see measure XXXX. Yes, absolutely. These are correct. So conceptually speaking, what this is going to do is make it so that if you flip all the qubits, then this whole thing picks up a minus sign, right? So let me draw that out. 0, 0, 0, 0 minus 1, 1, 1, 1. What happens if you flip all the qubits? Then this turns into 1, 1, 1, 1 minus 0, 0, 0. So flip all qubits. Can you confirm that you can see as I'm typing in this text box?
Yes, we can see.
Okay, great. And so that is exactly equal to minus the thing we started with, right? So the question is, do we get this minus sign if we flip all the qubits? If we started from the non-error state and flip all the qubits, we get 1, 1, 1, 1 plus 0, 0, 0, which is, of course, the same thing that we started with no minus sign. So the question is does this thing pick up a minus sign or not when you flip all of the qubits? So that's not an obvious thing to want to measure. It turns out, that that is exactly the same as checking whether an odd number of data qubits are plus. So there's a question, does a global minus sign matter? So the question is not, is there a global minus sign? It's what happens if you were to flip all of the qubits? Would you get a global minus sign? That distinguishes the states. Maybe, but I think a better way to do that, to think about this is this, are an odd or an even number of qubits in the state plus? This is not obvious. You can go through and work this out. But for those of you who are super comfortable with quantum mechanics and operators, this is measuring XXXX, and X, of course, is the bit flip operator. So if we measure it, we're getting an eigenvalue of the bit 4-qubit bit flip operator. So that's where the connection comes from. If that didn't make sense to you, you can take my word for it and work through the quantum mechanics a little bit more later. So that's the way that we pick up phase flip errors. The key point here is that under phase flip errors, all of these things go from having no minus sign when we flip the qubits to having a minus sign when we flip the qubits, which turns out to be a difference between an even versus an odd number of qubits being in the plus state. And so that is how we can detect phase flip errors. By designing clever codes that use superposition, the key point here is that the logical states all involve superpositions of the physical states. Using superposition of the physical qubits lets us detect phase errors in the logical qubits. Oh, sorry, phase errors in the coming from in the physical qubits. Phase errors in the physical qubits, not logical. My mistake. Yes, if we measure XXXX, you will collapse something. And we want to do that by measuring an ancilla. You can check that all of these things have the same eigenvalue under XXXX, so you would not collapse the logical state. You would just decide, is there an error or not? Okay. So how do we actually do the measurement? So let's go back to A1 first, right? We said A1 is supposed to be 1 if an odd number of data qubits are 1. And so we want to generalize the trick that we used before to find a quantum circuit that makes this happen. And I think somebody already mentioned this in chat. Keep tabs on time. Yeah, I should keep going on this. So here's the trick. We just we do a controlled NOT gate where we flip ancilla 1 controlled on each of the data qubits. And so basically there will be an even number of flips if there's an even number of ones. There will be an odd number of flips of the ancilla if there's an odd number of flips on the data qubits. And then we measure the ancilla, and we find out whether an even or an odd number of states are 1. Now, I'm going to leave it as homework to generalize the trick even further. to find a circuit that makes A2 equals 1 if an odd number of data qubits are plus. I strongly encourage you to play around with this. It's a good way to make sure that you understand the quantum mechanics, the quantum circuits that are required for this well. So I'll pause for just a second so people can take a screenshot or take this down if you want, but that's the homework. Okay, so a technical aside for those of you who are familiar with this stuff, and all of these things that we've talked about are called stabilizer codes. So I've been kind of going back and forth between talking about operators and syndromes and things like that. An n-qubit stabilizer code is one where all the syndromes measure mutually commuting n-qubit Pauli operators. So we have a fixed number, we have n qubits, and we pick a set of n-qubit Pauli operators on those, and that's going to be an n-qubit stabilizer code. Such a code can be defined by its list of stabilizers. And so, for example, the 422 code is defined by its list of stabilizers, which is XXXX and ZZZZ. There's a famous code called the 5-qubit error correcting code, which is defined by these 4 stabilizers. Most, but not all QEC codes that are widely used are stabilizer codes, in fact. So that's just a technical aside for those who are familiar with this terminology. And so basically everywhere that you hear stabilizer, think syndrome. Everywhere you think syndrome, hear syndrome, think stabilizer. I might be a little sloppy about which of these terms I use, because I'm only going to be talking about stabilizer codes, I think, for the rest of this. Okay, so we've seen a little bit of how quantum codes work. We've seen how to actually measure these syndromes. We've seen how we check for errors, which we do by measuring syndromes. And we see how we measure the syndromes without collapsing our nice data qubit superpositions by using ancilla qubits in a clever way and like control NOT gates and things like that. We've also seen how you detect both phase and bit flip errors. And the key with the phase flip errors is that you need to have your physical qubits in superposition when you're in your logical states. So now let's switch gears a little bit. Once we do those measurements, we have a decoding problem. We need to understand how we decode. So I'm not going to go into intense detail about this, but I want to kind of give an overview first of why the problem is hard, and then some of the architectures that are used for decoding. So the core problem of decoding is that I've listed some encoding, and I have a list of syndromes that I've measured from my quantum error correction circuit. And then I want to find what the most likely way to correct my qubits are. So there's some errors that happened. I want to find the most likely operation that will fix my qubits, so that I put them back into the state they were supposed to be in. So why is this problem hard? The first challenge is that the most likely error actually depends on the device. So this picture is a map of the IQM Garnet QPU. It's a 20-qubit quantum computer. It's available on our cloud service. And these circles represent qubits, and the squares represent couplings between qubits. The colors represent essentially the fidelity of different operations on the different qubits. So for example, the blue qubits are ones which have single qubit gates that tend to be particularly error prone. And blue boxes are ones that where the 2-qubit gates are particularly error prone compared to all the others. This is all on a relative scale. But compared to the others, certain qubits have more error, and certain qubits have less error. Certain couplers have more error. Certain couplers have less error. This is just normal heterogeneity in the fabrication and calibration process. But that means that depending on which qubits you're using, the most likely error might be different, right? If you're using qubit 12, the surrounding 2-qubit gates are pretty good. So they probably are less likely to introduce errors, but you're more likely to have had an error that was introduced from a single qubit gate on qubit 12. Whereas qubit 10 is the opposite, right? It's more likely that 2-qubit gates introduced errors rather than single qubit gates. So you need to build what's called a noise model. A noise model tells you what errors are more likely on which qubits. These are generally built from a combination of theory and device characterization. And most decoders require some sort of noise model as input. The better the noise model, the better your decoder will perform. So the decoder we're going to use tomorrow is going to use a really simplistic error model. It's just going to assume that certain sets of errors are just completely equally likely. But when you really have a real device, you want to characterize your noise model very effectively so that your decoder can be more effective. Now, the other thing, and this also means that if you want to do QEC, you want your calibration to be as stable as possible. So you don't want to have to constantly recharacterize your device so that you can readjust your noise model so that you can readjust the decoder. Superconducting qubits tend to actually be quite good at this. So IQM qubits in particular have been incredibly stable over fairly long periods of time. I'm talking, like days periods of time here, where recalibration only makes very small effects on the device. Now, second challenge, there's other more complicated errors, and you have to account for these in your decoder. I'm going to highlight 3 different complicated errors. One of them is called a correlated error. So an uncorrelated error would be, let's say we have an error that happens here, and it flips a single qubit from 1 to 0. A correlated error would be an error which happens, let's say, because this qubit on the right had an error, this qubit on the right, it tends to cause this qubit on the left to have an error. And so it's more likely that errors are going to happen as both of these qubits flipping than just one of them. And your decoder has to be aware of which of those errors are likely. And these correlated errors or crosstalk, crosstalk especially comes from gate errors where you accidentally mess up a qubit that you weren't trying to affect. Your decoder has to be aware of these sorts of errors if it wants to be as accurate as possible. Now, another type of error, and these are some of the ones that are the most dangerous, are called leakage and loss. So leakage comes from the fact that most qubits don't actually just have 2 states. There's actually, let's say, 3 or 4 or 5 or infinite states. And we try very carefully to make sure that we don't accidentally take the qubit and move it from the states 0 and 1 up to state 2, because we want a qubit, right? A qubit is supposed to be 0 or 1. 2 doesn't even make any sense for a qubit. So leakage happens in a large number of different applications. Modalities. Exactly what the nature of 0, 1, and 2 are changes by modality, but it's very, very common that you have these extra states in there. And these have to be dealt with in decoders. This is not as simple as looking up in a table what happened. An even more severe version of a leakage error is a loss error, where basically something comes in and just takes one of your qubits and knocks it out entirely of the system. Now, this doesn't happen in superconducting qubits because we pattern our qubits and they just kind of sit there on the chip. You don't have something that's going to delete a qubit from the chip. For things like trapped ions and neutral atoms, this is a much more significant issue that they have to be concerned about in dealing with these errors, because they can lose qubits. They can have atoms that kind of just float out of the traps. Okay, so I'm going to pause for some questions. How can an error correction code not be a stabilizer-based code? Doesn't it mean that the measurement will influence the data? Not necessarily. You still have to be careful about what you're doing exactly. But with careful choices of measurements, you don't necessarily have to have have to have stabilizer codes. You just have to be very careful about your encodings and what sorts of syndromes you're measuring. What 2-qubit gate is used here? The native 2-qubit gate on IQM machines is Control Z. Is 2-qubit gate the only source of crosstalk error? No. In general, things like initialization and readout pulses can also cause crosstalk, I believe. Can leakage be avoided with atomic qubits? Generally, no. So leakage is still possible in other qubits. Atomic systems often have a number of other states that do exist as well. Right? If you have an atom, your electrons can be in principle infinitely many states. But the way that the exact way and frequency in which leakage occurs is different from different atomic versus superconducting qubits or other modalities. Would leakage be a feature, not a bug, when using qubits? Yes. Well, sort of. You don't want to accidentally if you're using qubits, you don't want to accidentally put your qubit or your qubit into state 2 when you didn't mean to. But you do still want to put your qubit into state 2 sometimes. Now, if you're using, let's say, qtrits, so 3-state systems, you still could have leakage, which is you accidentally send your qubit not to 0, 1, or 2, but to 4. So leakage doesn't disappear when you're using qubits, but it changes the nature of the error correction problem. How can leakage and atom loss be modeled in a noise model? That is something that's a little beyond the scope of this. That's a much larger question in itself. Leakage-aware decoding is as far as I'm aware, a very large topic of current research. Is qubit loss better for error detection than Pauli errors? It's very easy to see that qubit loss happened. It's very hard to fix qubit loss because your qubit's just gone. There's nothing to correct. So I would say that for error correction, Pauli errors are way better than leakage or than qubit loss. Like qubit loss is one of the worst things that can happen for error correction. It is a very easy error to detect, though. That is true. Is there any type of QEC that is independent of type of errors? Do we have noise models which can represent any type of error, leakage, loss, or correlated errors? That is something. Yeah, these leakage and loss-aware decoders. I don't know enough about the details to tell you if there's really a universal decoder for a particular code. And as you'll see, the type of decoder depends on the code as well, which is a choice. So there's like many choices here. You have the physical system, you have the code, you have the decoder. So lots of different pieces. So the way that all these things interplay is quite involved. Any comment on QEC using FPGAs? Give me a few minutes, I'll get there. Please explain how the calibration cycles work. What is measured and how? So calibration is basically a bunch of experiments that say, if I do X to my qubit, how does it respond? And the way that calibration works is going to be different for different physical implementations. But in the context of, let's say, superconducting qubits, basically there's a bunch of experiments that say, well, actually more generally, you say, okay, I'm going to try to understand how my qubit flips depending on the electrical pulse, let's say, for superconducting qubits you get. Like if I send in a pulse of this length and this amplitude, what happens to my qubit? Now, okay, I've figured out that how to flip my qubit in a very coarse way. Now let me see if I can do it really precisely. Now let me see if I can figure out how to do a CZ gate, things like that. So it's a sequence of experiments that basically tune all the parameters of the electrical pulses that control the quantum computer. For superconducting qubits, for IQM devices, this calibration happens typically once or twice a day, depending on the user's preference, and for about 45 minutes, give or take. And for they can go a lot longer without calibration and still maintaining fairly stable performance. For other systems, calibration can take a lot longer, or it can have to happen more often. The other thing to point out is that at least for IQM, we have manual calibrations and automatic calibrations. Automatic ones are the ones I'm talking about, and that keeps the system running very well. Very rarely do we have to manually calibrate. Manual calibrations are very laborious. Different systems have different calibration requirements for that. Can calibration cycles be thought of as stabilizer measurements? No. Calibration cycles are much more analog experiments. So for example, you would measure the frequency of an electrical pulse, and you sweep a frequency of an electrical pulse, and you figure out which frequency your qubit responds to most strongly. That's not a stabilizer measurement in any sense. You have to do calibration in order to talk about measuring qubits in your Z basis or in your X basis or something like that. Let's see. Couldn't you have a phase error or a bit flip error that's a fraction of a pi rotation in the Bloch sphere? Yes, you absolutely can. Here's the magic. So this is going back a bit, but this is an important point, so I'm gonna go back. The key point here is that, let's say here, we check if an odd number of data qubits are, let's say, plus. Now, it's possible that if you do a fraction of a pi rotation, what will happen is that your qubits will now be in a really bad sounding error state. They'll be in a superposition of having an even and an odd number of pluses. But the magic is that when you measure whether there's an even or odd number of pluses, you will collapse the wave function into a state that has an even or an odd number of pluses. So basically what this will do is this will throw out half of the possible error states in a rough sense. It will randomly switch you to a state, the part of the state that has no error, or the part of the state that does have an error. And if there, a discrete error, like an odd number of data qubits, it's a pi rotation. So by doing these measurements, you actually go from analog errors into discrete errors. I think been a couple of questions about this, so I should add a slide on this in the future. But it is really interesting, actually. It turns out that you do get a positive benefit from measuring the ancilla here. It actually collapses the wave function in a way that's helpful to you. It turns analog errors into digital ones. So does syndrome measurement discretize quantum errors? Yes. How quickly does the calibration drift? So it depends on the system. So some systems in existence become horribly uncalibrated after a couple of hours, and you have to do a really massive calibration again. IQM systems drift very slowly. If you didn't run calibration for, let's say, weeks, we've done this before, the calibration doesn't drift super strongly. The thing that would be a problem is if you had a power outage, let's say, and the cryostat warms up. But that's pretty dramatic problem to have. Does somebody who knows codes for spin-based quantum computing systems build codes for superconducting quantum systems? Yes. There is a lot of hardware, software, or like hardware and code interaction, but once you are comfortable with QEC and building codes, you can certainly contribute to building codes for superconducting quantum systems. There's a lot more to there's a lot that goes into code design and theory of quantum codes and things like that is at least translatable between systems. Okay, good. Okay. So the other thing that I wanted to mention here, the next challenge to decoding is speed. So I said before that we have to do quantum error correction on pretty fast timescales in order to do real-time decoding. We're talking, hopefully nanosecond timescales to keep the speed of superconducting qubits like let's say hundreds of nanoseconds, something like that. So let's give an estimate here. So roughly, let's say we have 10,000 logical qubits, and each of those logical qubits has, let's say, 50 syndromes per logical qubit. That's actually a pretty large number for some applications, and it's reasonable or smallish for others. So now, what's the rate? We generally measure let's say we want to measure these syndromes at about 1 per microsecond. And this is a pretty reasonable data rate that you want in order to actually operate at the sorts of scales that superconducting qubits can. Now, what this means is that you are processing 500 gigabits per second. Now, 10,000 logical qubits is a large quantum computer. That's like real. If we had 10,000 logical qubits, then we're rolling to break encryption and all sorts of applications like that. So this is a serious utility scale quantum computer. But this is the sort of data rate that we're looking at to have a serious utility scale quantum computer. That's a fast data rate to be processing. So we really need to be processing a lot of data very quickly in order to do real-time decoding. So not only do we have to have our decoders be accurate, but we also need them to be very efficient, and they need to be able to process data extremely quickly with extremely low latency. So with that in mind, actually, I will come back to this 500 gigabits a second thing in just a moment. But before that, let me mention types of decoders. So this is a software question right now. So here's a table of decoders from a recent paper. There's a lot. They have lots of pros and cons. They have different speeds, all sorts of different things. So I'm going to just mention a few of them to give you a flavor for the sorts of different things that you can do for decoders and where there might be benefits and drawbacks. So let's start with a lookup table. So here's the simplest decoder. We saw before, let's just do our repetition code to give you the idea, right? We say, okay, we look at the syndrome for qubits 1 and 2. Are they the same or different? We look at the syndrome for qubits 2 and 3. Are they the same or different? And once we know that, we know what we should do to fix the error. We pick a qubit to flip or do nothing. This is great. This is easy to program. It's easy to understand. The problem comes in scaling. Imagine that we want to be able to catch more errors. So instead of doing a 3-bit repetition code, we do a 4-bit repetition code. Then instead of 4 possible syndromes, we get 8 possible syndromes, which look like this. And our lookup table gets more complicated. And in fact, the lookup table gets exponentially more complicated. And so lookup tables in general are fast, they're easy to implement, but they have exponentially bad scaling. When you're looking at, many qubits and like large codes, things like this, it becomes extremely, extremely difficult to do this scaling. And many logical qubits, you start running into these problems. So lookup tables are generally not used in any practical situation because they just scale really, really badly. Now, the decoder that we're actually going to use tomorrow, we're not going to go into the details of it because there's a wonderful Python package that everyone uses for it, is called minimum weight perfect matching. So the way to think about this is, here's a grid. Imagine that this grid represents places that an error, represents syndromes. So you're measuring a bunch of syndromes in different places in space. And roughly speaking, each line in this picture is a way that an error can occur. So this is a little more complicated than a specific qubit that can go wrong. But roughly speaking, the edges in this graph are ways errors can occur, and the dots are syndrome measurements. And so the idea is that if we have a syndrome that found an error, again, roughly speaking, We want to find a set of errors that explains this pattern. And we want to do that efficiently. Now, for certain types of codes, what that means is finding a perfect matching. So it's finding a set of edges that connect, or a set of paths that connect pairs of these codes. And basically what this says is that on each of these red edges, we would do a correction. And if we did those corrections, then we would fix our error and we would understand what was going on. So this is a minimum weight perfect matching is a common graph theoretic algorithm, which has been applied to QEC. And it turns out that this is extremely fast and practical for specific types of codes, including the one that we're going to work with tomorrow, the surface code. The negative here is that it doesn't naturally generalize to other codes. And the surface code we'll talk about tomorrow. It's got benefits and drawbacks. But if you don't like those particular drawbacks, then minimum weight perfect matching may not be for you. Now, another decoder is something called belief propagation. And this basically is an algorithmically speaking, it looks like this. It's message propagation between the datas and the ancillas. So the data qubits say to the ancillas, I think I'm in error with probability P. The ancillas take in that message and say, given my syndrome and what I'm hearing, you should update your probability. You're more likely or less likely to be in error. Then the data qubits update their belief based on the various ancillas messages. So, data qubit 3 would listen to A1 and A2 and update its probability after A1 listened to D1, D2, D3, so on and so forth. And once the data qubits update their messages, they talk back to the ancillas and say, I'm in error with a new probability. And the ancilla says, you should update your probability, iterate until converged. And once we do that, we can say where the most likely errors occurred based on what the data qubits think about their probabilities. This is very fast and it scales well, but it depends on the code design. It turns out that specific ways for the code to be designed, which is actually very common in a lot of codes. Specifically, there's a loop in this graph here of the way that the data and ancilla qubits are connected. These loops can lead to incorrect results. So you have to. So these belief propagation decoders are also better or worse for different types of codes. Now, the last decoder I want to mention is machine learning or AI decoders. So we said we want to take a list of syndromes and get the most likely correction out. So let's just stick a neural network or some other form of AI in between. And we can train it. Great, this is something that you can absolutely do. And it turns out that they're actually very fast and can be extremely efficient. The problem, of course, is that the training is very costly. And depending on how much information you're putting into the training, this can be incredibly difficult and costly to do. So it's now the end of the 3 hours. So I have just a couple of I have about 3 or 4 slides left, which I'll go through very quickly, if that's okay, and then just a couple of resources, and we'll wrap for the day.
Yes, I would say maybe we can go over to finish the slide, and for questions, please, we can follow up with them tomorrow if the audience has more questions. Yeah,
perfect.
Please go ahead.
All right. So, what are the hardware approaches to decoding? So, as we saw before, there was this estimate that at scale, quantum computers are going to do error correction, are going to have to process 500 gigabits a second at with extremely low latency, because this is not just processing this information; it's also feeding back into your quantum circuit. So, one thing that we could do that's being investigated is, let's take our quantum computer and let's take an HPC, some HPC, and let's hook them up. And so you can work on this sort of tight HPC integration for error correction. And I should mention, I'm about to mention 3 different error hardware approaches, And these hardware approaches are all being pursued right now. None of them have won yet. So and it's not clear that any of them is going to win in the end. So we'll see what happens. This is a massive open research problem right now. Now, second hardware approach is with built-in compute. So this is basically doing some more specialized compute that's sitting inside your quantum computer. Maybe that's FPGAs, maybe that's GPUs, maybe that's application-specific integrated circuits, whatever it might be. And so whether we need HPC or built-in compute will depend on applications. It will depend on what ends up being able to handle the particular technical constraints we're looking for. It depends on how fast all of the error correction happens in like the commands for the error correction happen in software, interfacing a lot of things. There's a lot of things to deal with here. And another one is AI decoding, where we have maybe a supercomputer that is training an AI, and that can maybe be done classically and maybe a little more slowly. And then that trained AI can work quickly, and that sits on some standard classical compute that we're using inside the quantum computer that is being used for inference. And then we update this AI, say, as the calibration changes or something else like that. So all of these approaches are being investigated. It's still not clear which of them are going to work well because there's still a long way to go in developing this field. But I wanted to highlight some of the frontier ideas in the field. So that's the end of my content for today. As a reminder, today we have done a big picture overview of quantum error correction. And then we introduced a couple of very simple quantum codes, the repetition code and the 422 code, and looked at decoding for them and kind of the core problem. So tomorrow we're going to be doing a QEC experiment on the quantum computer, and you have some optional homework. This notebook is written in CRISP, and if you want to get comfortable with quantum circuits in CRISP, I encourage you to take a look at this the notebook that is in this GitHub repo so that you can play around with that. Go ahead and download that and take a look. So I'll leave that up for just a moment long. Actually, I'll come back to that one in just a second. A couple of additional resources that I want to flag to everyone. So again, you can sign up for IQM Resonance and get bonus credits here, so you can play around with our quantum computers. And the notebook here runs things on those quantum computers, so you'll get on there immediately. The notebook is in Jupyter. It is a Jupyter notebook. And if you're not sure how to start, we have some resources for you. We have IQM Academy at iqmacademy.com, which is a free curriculum and learning platform for anyone that assumes no previous knowledge. It's also got a lot of tutorials on programming with quantum computers and a lot of interactive modules. We also have a community Discord. So here's the Discord link. Chat about your latest project or get help from IQMers or other IQM users and stay in the loop about our events. And I just wanted to flag as well a couple of nice resources for QEC reading. This is my personal opinion. There's a couple of really nice textbooks. One is Mike and Ike, Nielsen and Chuang, which is a classic textbook in the field. They've got a nice chapter on QEC. Gottesman has a full textbook on QEC that's freely available online that I really liked. And I found these two recent papers very helpful, especially when looking at some of the more frontier ideas in QEC to get kind of a foothold on the literature.